Okay, thanks, Fred. And I don't think Gerry needs any introduction, but I'm sure we've all either seen one of the many articles in the national publication on his layout, or had the pleasure to see it in person. So, Gerry's up in Cincinnati with the Division 7. So we really appreciate him agreeing to give us one of his great clinics. So Gerry, thank you very much, and we'll let you take it away.
Okay, Russ, thank you very much. This is a first for me to give a virtual clinic. So if you've got any questions, I'd suggest you get on the chat and put the question there. And I think Ron or Fred or somebody is
Yep.
monitoring that chat list. Normally, I would say just interrupt me, but since we're all virtual, we're just going to go ahead and go right through it, and I'll take questions at the end. So DCC, when I first encountered DCC, it was a mystery to me. I didn't know what it was until I got a hold of a vendor who, or a dealer, I mean, who helped me out and educated me a little bit. And then I have just acquired a whole lot of knowledge by experience. And I'm going to tell you right now, experience is a lousy teacher. You have to have the bad experience before you get the lesson. So I'm going to try and help you guys out and with however I can with DCC and with just generally the electronics of the hobby. And as you can see on the front page there, we've got some guy flying a kite with a key on it. And I think you all remember the Benjamin Franklin thing. So we're going to talk a lot about electricity in general, and then zero in on DCC. Just by way of introduction, I'm an electrical engineer, and this cartoon appeared in the IEEE mini conductor a long time ago. And I can use this, though, to kind of highlight or emphasize what I want to talk about today. You notice the electrical cord there is a physical connection. You can touch it, you can feel it, you can bend it, you can plug it in, that sort of thing. But what goes on behind the outlet is abstract. Electricity is abstract, and if you try and touch it, you will know that it is a real thing, but you can't see it until you actually feel it. So let's go on and talk about the differences between the physical and the abstract. So I'm going to talk about, I'm going to just use a boxcar and basically electricity to highlight the differences. Boxcar obviously is very tangible. You can pick it up and you can feel it, you can run it on your rear road and that sort of thing. Electricity is abstract and it's really intangible. The function of a boxcar is to carry goods and roll in a train and all that sort of thing. And the function of electricity is to perform work. You might not have thought of it that way, but that's what you want electricity to do, is perform work. And a boxcar you observe by sight and sound and all that sort of thing. And electricity is observed by results. You light a light bulb with it, or you run a train with it, that sort of thing. So you can only observe electricity by its results. You can measure a boxcar with a scale. We all kind of want some measure of the weight of our cars, and you can measure them with a tape measure, that sort of thing. You measure electricity with other electronic devices. So you need some sort of a device to measure electricity. And the attributes of a boxcar are road name, era, capacity, all that sort of thing. And the attributes of electricity you can trace down to AC, DC, DCC, and then you can get into other things, high voltage and RF and all that sort of thing, radio frequency stuff. So here's what my objective is today, is to demystify electronics, or DCC, make it less abstract for the general model railroading community. And we're going to do that by examining the basics of electronic concepts. And then we're going to make DCC less intimidating, if that's possible. But at any rate, we're going to examine DCC attributes versus basic electronics, and I'll define that later. And we'll provide some clear, concise definition of terms. Some of these definitions are my definitions, but nevertheless, I had to use some very clear, concise documentation to build and maintain my railroad. So that's very useful in that regard. And we're going to provide some practical, logical wiring practices. I hate seeing a rat's nest of wires, and so I have doggedly avoided rat's nests under my layout. So, and then last but not least, we're going to talk about providing the basis for a signal system. So that's a minor part of this presentation, but if you are a signal buff, we can look at that. So what we're trying to do is build a mountain here, you know, just like the Egyptians built pyramids. We're going to start with a base here, and we're going to put layer on top of layer on top of layer. So bear with me, and we're going to start, we're going to go through DC from batteries, and then we're going to talk about AC, alternating current basics. Then we're going to talk about, actually, I'm going to probably just jump over the DC, getting DC from AC. Then we're going to talk about DCC with regard to AC, and then some layout wiring practices, and we're going to go through device hierarchy and all the things you see there. And then detector wiring, which would prepare you for signals. And then I'll talk a little bit about neat, cool, and tidy wiring practices, color codes, wire sizes, etc. And the thing I want to mention here about DCC, all of these topics right here are vendor independent. It doesn't make any difference whether it's Digitrax or NCE or whatever. All of these topics are vendor independent. I will get into cab buses, and that's the difference. There are very, actually profound differences between vendors in that regard. As I go through this clinic, the white boxes at the bottom or sides or whatever are takeaways, which I feel is some practical information, some useful tips that you could have. And Fred has a link to this PowerPoint that he can share with you, but I guess since you guys are on top of the technology and have YouTube videos and stuff like that, you can probably just watch the YouTube. So, Fred will publish the link to this PowerPoint in some form or other. So let's talk about batteries. It's the simplest form of DC, direct current. And this really goes back, way back to 200 BC, maybe even longer ago than that, because archaeologists found a jar in Baghdad, over near Iraq now, and determined that it was a battery. Then that the people back then were using it to electroplate gold onto silver objects and other objects like that. So it's basically a battery is two dissimilar materials connected with an electrolyte solution, which you see down in in this area of the battery. So now this is a little quiz. Back in 1800, an Italian physicist created a voltaic. We get the term volts. Actually, the IEEE and some of the electrical engineering societies have taken people's names and attributed them to some of the measurements that you would get. And so that's where we get our term volts from. Now, the word battery was actually coined by somebody relatively recently. Well, I shouldn't say way back in the 1800s. And if you take a look at these diagrams, they had they could construct batteries by connecting these cells of dissimilar materials in electrolyte solutions, and they would connect them together with copper wires, and that's where we get the symbols from here. You have several cells here. You have actually in this representation just 2 cells. So the word battery was coined by Benjamin Franklin, because he was an experimenter and saw these Leyden jars and actually experimented with Leyden jars. And he felt that these Leyden jars, as they were all lined up, reminded him of the rows of cannons on Battery Park at Manhattan. So if you've ever been to Battery Park, you know that it's right at the tip of Manhattan, and it guards the entrance into New York. And so it was a great place to put a battery of cannons. Okay, so we know that railroads have used batteries for telegraph way back when, and signals and all that sort of thing. And modern hybrid locomotives, gensets, and all that sort of thing use very large arrays of batteries. And now, of course, we're getting into electric vehicles, EVs, on the highways and stuff like that. So battery technology has come a long way. For our model railroad use of batteries, if you're using a 9-volt battery, I recommend nickel metal hydride, which is rechargeable, and get a charger and just keep them on charge, and you can put them in your throttles or wherever you're using them, and they last a long time. That's not the highest density charge, but nevertheless, it's very practical for model railroading use. So let's talk about AC versus DCC. Alternating current looks like this. This is a picture right off of my oscilloscope, my old oscilloscope. And it's from the output of a 14-volt transformer. This transformer was used to power one of my, actually my command station. You notice that it goes positive, and then it goes negative, and then goes positive, etc. And so if you measure the time between cycles, this is one full cycle right here. It's 1/60th of a second. And actually, you can see up here in the right-hand corner, it's 16.6 milliseconds, which turns out to be 1/60th of a second. And so if you want the number of cycles in a second, you get 60 cycles. So our power coming out of our outlets is 60 hertz. Again, that's a guy's name. Hertz was attributed to the frequency of alternating current. So let's talk about what AC provides. Alternating current provides power. So obviously, everything we run, including the computer you're looking at right now, is powered by alternating current. But it also provides accurate timing. The power company is very diligent about maintaining 60 cycles per second. If their generators run a little bit faster, they will slow them down a little bit to keep it averaged out at 1/60th of a second per cycle. And some of our clocks still run on 60 hertz. It keeps time by counting the number of cycles and keeps time progressing on your clock. So let's talk about DCC now. You'll notice that a DCC signal, well, first of all, the first thing I want you to note is that the scale, the vertical scale here is the same with this trace and this trace. And so here you have a DCC signal, which is, you notice is square, and you notice that the cycles are different. It is not a consistent width of a cycle. And so the NMRA has established a recommended practice 9.2, which defines the width of a 1 and a 0. So all of your computers, the computer you're looking at right now, are run with 1s and 0s, and your decoders in your locomotives are run by 1s and 0s that your command station puts out. So the scale of this is 14 volts, but because it has a positive side and a negative side, positive, negative, just like over here on the AC side, positive and negative, you want to measure your DCC with an AC setting on your meters. So DCC provides power. It's just a square form of alternating current. So you can light light bulbs with DCC. You can light LEDs with it and that sort of thing. You can do a lot of things with the DCC signal that comes out of your command station, and not just run locomotives. And of course, the DCC provides information, 1s and 0s, and that's what your decoders run on. And so here, this is just 14 volts AC, and you notice that there's this peak goes up to about 22 volts over here. And it goes above the 14 volts because the AC is measured in RMS, root mean squared, but you can just say it's an average. So whatever goes up above the average is taken care of by what falls below it. So one other thing here is use the AC setting on your digital multimeter when you're measuring your track voltages. And so here's an example of a meter. And if you're going to go out to Home Depot or Lowe's or someplace like that and get a multimeter, you can get them really cheap now. Make sure it has a DC volt reading. Make sure that it has an AC volt reading. Make sure that it has a current reading, and this is on this particular meter, it's DC current. And if you get a really good one, you'll be able to measure AC current, but this meter doesn't do that. So I've got one that does, a different one, but this lacks that capability. Make sure you can read resistance and continuity. So continuity, when you touch the two probes together, you will hear a beep, as evidenced down here on this setting right here. So again, for DCC, use the AC setting, the alternating current setting on your meters. Okay, so now we're going to talk strictly about DCC. Oops. What I'm going to use is a home wiring analogy for power hierarchy in DCC. So this is a picture of the transformer that's outside my house on a pole. And that wire right there is bringing in 7,500 volts to this transformer, and there's another ground wire, a return wire there, and there's a circuit breaker on this connection going into that transformer. But then there's also out of the transformer, you see these 3 terminals right there on the transformer. These wires that are coming down here, coming down the pole, are 120 volts or 240. Between this terminal and that terminal is 120 volts. Between this terminal and that terminal is 120 volts. So this is what's called the neutral, and these are the hots. And between the 2 hots is 240 volts. That's why it's double rated that way. So coming down, those wires coming down go to a power disconnect and circuit breaker that's on the side of my house. And so this circuit breaker is a service disconnect. If you flip that down, the power goes off to the house, and it's a 200 amp circuit breaker. Now from that circuit breaker, it comes into the house and goes to a circuit breaker panel, and there's multiple circuit breakers in this circuit breaker panel. Each one of these is about 20 amps, and there's some higher amperage ones down here. And if you think about it, if each one of these is 20 amps, there's more than 10. So I could, it does. Let's put it this way: each circuit breaker is set to break at 20 amps rather than adding it up all to 200 amps. So you don't want to break this breaker here. You want to break it at a lower level. And then from those circuit breaker panels, you go to outlets. And this happens to be a ground fault outlet, which is a safety device for anything where you could be grounding yourself to a water pipe or something like that, and that will trip also. So I'm using this analogy because this big transformer here and this big circuit breaker is sort of like your DCC booster. It's taking power and bringing it, your power supply, your transformer is bringing it down to a usable level, and there is a breaker in your booster, and then you've got your circuit breaker panel here, which is basically your other circuit breakers that you could use to break it up rather than trip this big one. You don't want to trip this big one. And so this is like a power district circuit breaker on your railroad. So let's look at this hierarchy here, specifically with DCC. You've got your command station, and your throttles attach to your command station. So your throttles are what is connected, telling your command station what you want to do with the railroad, with a specific locomotive on your railroad. And so then out of your command station, the actual command station is just a little bit of the circuitry. Out of your command station, you've got boosters that also have circuit breakers in them. And in most cases now, most manufacturers put a booster and circuit breaker along with the command station in one box. But you can also have a separate box or booster out external to that, and that is what your control bus connects to. So now here is a representation of the power supply, the transformers that are used to power these devices. And from a booster, you go to, let's say, individual circuit breakers. So this is what I am recommending, is that out of every booster, you break it up into 2, 3, 4 different circuit breakers that would go then to your track sections. In your on a model railroad, you would only have one command station, but you can have multiple boosters. You can have as many boosters as is needed by your railroad. So this is what, again, this is part of my definition, but I think most model railroaders use this definition. You've got your boosters basically form your power districts. So in this case, over here on the left-hand side, I'm calling this power district number 1, and I'm calling this power district number 2 for this example. And then these individual circuit breakers down here, I'm calling A, B, C, and D. But for nomenclature, for documentation on your railroad, I'm calling this power district 1A. P1A is going to this block or area of the railroad, P1B, P1C, etc. Now, because of the control bus here, you can take the booster and put it out anywhere you want to, and I recommend putting the booster out near where it's being used. The signal that's on the control bus here is a very low level, low power signal that comes out of your command station and goes to the booster. And the booster, all it does is amplify that, not necessarily in amplitude, but in power. So the signal that's on the control bus is only a few milliamps, whereas you can get up to 5 amps, 8 amps out of a booster. And that's what the booster is. It's just a dumb electronic device that is amplifying the signal coming off of the control bus. One of the cautions here is to make sure that if you do have multiple boosters on your layout, that you maintain the same polarity between all of your boosters. If you don't maintain the same polarity, and that you've got 2 wires on the control bus, you're going to be having the signal on this booster P2 inverted from what is coming out of P1. You can run a locomotive in P1 just fine. You can run a locomotive in P2 just fine if the polarity is reversed. But when you try and cross over from P1 to P2, you're going to cause a short because they are opposite polarities, and that's not desirable. So make sure that you keep the same polarity going into your boosters. Another aspect is grounding. And this is one thing that I suggest you consult your DCC vendor's manual to see whether they want you to ground it or not. I use Digitrax, and I ground all of my boosters and command station together. Basically, your wall outlet here has that 3rd pin, which is a ground to your house ground. And doing that, having this booster P2 grounded to the same ground as P1 keeps them from floating and being having voltages built up between the two. It just keeps them all together, well grounded, if you want to say that. The other thing is when you are powering a booster, if you've got a 5 amp booster you want the power supply, the transformer here, to be able to supply at least 5 amps. I would recommend an 8 amp power supply. And my standard up until a few years ago was a MagnaForce MF615. This all comes together. It has a power cord with an outlet that has the grounding, and then it has a ground that comes out of the power supply, and you can just ground that to your booster. And it is an 8 amp power supply. MagnaForce 615s are not made anymore, and I haven't been in the market to buy anymore, so I'm not sure. I think NCE has a good power supply like this, but you're going to have to search the internet to find a good power supply or transformer for your DCC systems. Now let's go back to the tracks. Between circuit breakers here, you want to gap both rails. And I'll tell you why, because also if you want to put a switch to kill a particular power section on your railroad, kill both of the rails, both of the wires go into both rails, and have the gaps between both rails. Now, one practical example of that is when we were building and wiring my railroad, we were working on other stuff over here, running trains, staging, or whatever it was. And another fellow was doing some soldering, some drops in this P1D over here. And so I turned off the power to P1D, but I had a switch only on one rail of that. And as he was soldering, he was saying, "Hey, wait a minute, I thought you turned this section of railroad off. I'm drawing arcs." So as his soldering iron was touching the rail, he was drawing an arc. And it all of a sudden dawned on me that I was only breaking one rail. So I highly suggest you break both rails to turn off the power to a particular section. And another big thing, I recommend that you put fans on your boosters. The Digitrax boosters and command stations have fins on the back. And I draw quite a bit of current out of the boosters, and the boosters were faulting at one point. And I realized it by touching one of them, and those fins were really hot. As soon as I put a fan on the boosters and cooled those fins, everything just hummed along just fine. It was really a great discovery on my part. And so if you're drawing a lot of current out of your command stations or your boosters, I'd recommend you just put a fan blowing a little bit of air across them. You can get these little fans. They're 12-volt DC fans from Newark Electronics or any other electronic outfit. But just make sure they're the square 12-volt DC fans, and you can power them right off of the booster by rectifying it and feeding it right to the fan. Now, once we've got our command stations and boosters set up, we got to wire our track. So here's again. I'm using some recommendations here, which I'm going to kind of negate as I go through here. But I recommend that when you have your track bus, you see a pink wire here and a purple wire down here, then you have different colors for those tracks, the track bus. And I knew that I wanted to do this, so I called my local distributor when I was starting to wire the railroad and said, what color wires do you have 12 gauge stranded? And I would recommend you use 14 gauge stranded. 12 gauge is overkill, but that's what I used. So I asked him what colors he had in stock of a 500-foot roll. And I said, I don't want to use standard house wiring colors. Your house wires have colors behind the outlets there, white and black and red and green. And I didn't want any of those colors. So he looked at his computer. He says, well, I got pink. I said, okay, give it to me. Even if it is pink, okay. And I've got purple, so that's the standards that I settled on. So all of my rail A connections are with pink wire, and all of my rail B connections are with purple wire. And I use stranded wire because stranded wire can carry more current than solid wire. A 12-gauge stranded wire can carry more current than solid wire because, believe it or not, the electrons are carried on the surface of the wire, not necessarily through the wire. So when you've got strands, you've got a whole lot more surface than you do in a solid wire. And I also use these insulation displacement connectors heavily, and I will tell you why here in a second. So I used wire colors that avoid the NEC, National Electric Code standards. And I used stranded wire for the reasons that I just said. And when I wired the layout, some people, a long time ago, and I don't know why, they suggested that you take your track bus wires and you twist them. And I highly recommend you do not twist them. Number one, what kind of a problem are you trying to solve by twisting them? Unless you've got a problem, let's not try and solve it. And secondly, I taught electrical engineering at the University of Dayton, and one of the courses that I taught was network synthesis. And when you twist wires together over a long distance, what you're doing is creating a transformer. And so you've got distributed inductance and capacitance along those twistings, and that can cause problems for your DCC. And then from the track bus, then you're going to drop down feeders to your track. I use 20-gauge solid wire. Obviously that's not mandatory, but then what that made it practical for me to use these Scotch lock IDC connectors. Let me go back here just a second here. These Scotch lock IDC connectors, so that taking the 12-gauge wire through the IDC connector and then dropping down a 20-gauge wire, actually two 20-gauge wires, I could connect these two over here together in one Scotch lock connector, or just double it over. When you use an IDC, an insulation displacement connector, make sure that you've got good connections with that they aren't loose. And so I use a pair of feeders for every section of track. If you're hand laying track and you've got your lengths at 3 feet, or even if you are using prefab track, if you get a 3-length section, even if you solder those sections together, I would still suggest you drop a feeder for each section. Number one, don't trust a rail joiner to make electrical contact. If you do that, you could. I would suggest you solder those rail joiners in, connecting those rails. one of the things to keep in mind is that nickel silver is what we use now. We used to use, if you're old enough, like I am, we used to use brass rail, if you remember that. And brass is a really good conductor, but it oxidizes. It oxidizes very quickly. And so you can be running trains one day and come back a week later and you can't run trains because that brass rail has oxidized. So nickel silver is used today because it does not oxidize. And but nickel silver is a very poor conductor compared to copper. So all your track bus and your feeders here, they're copper, but your rail is nickel silver. So if you have a long block or long piece of track, if you only connect your feeder at one end, by the time you get to the other end of that track, you're going to have a volt or two of drop, voltage drop by the time you get to the end of that track. And decoders don't like that. So I suggest that you have a drop every 3 feet or every section of track as you're wiring it up. And then all of my connections are IDC connectors at the bus level. Of course, you got to solder the feeder to the rail. But the track bus generally is underneath the layout, and I would highly recommend you not solder under the layout, because molten solder dripping down into your eye or other parts of your anatomy is not a very pleasant experience. And of course, experience is a lousy teacher, and so I learned by experience. But anyway, and then so I use IDC connectors under the layout. Now, if any of you are not interested in signals, this would be a good time to take maybe a 5-minute break. But those of you who might be interested in signals, we're gonna look at this. If you're going to have signals, you want to have block detection. And so here is how I recommend you wire your blocks. You have, again, your pink and purple wire here for rail A and rail B. Then now you're going to take your, this is all off of one circuit breaker. You're going to break your track up into blocks. And so I recommend you put a, you break the only one rail of, and you can use either rail A or rail B. So then you come off of your track feeder with block feeders. So this is a block feeder on the left-hand side here. And you got block feeder here. And then from your block feeder, you drop down to your track. So I'm calling this block 1. I've got 3 drops to block 1. Then I got a break. Now I'm having another block feeder to block 2 and block 3, etc. So now the detected rail, one of the takeaways here, detected rail can be either rail A or rail B. And so this is now your block bus. This is your track bus. This is your block bus. And these are your track feeders, your block feeders. Gap 1 rail. The opposite rail becomes your common rail. And use IDCs, again, for the same reasons before. And if now well, let's put it this way. Now you have to have some way of detecting current that is flowing into that block. And so I am emphasizing to where to put the current detector. Whoops, wait a minute. Let me get back here. Where am I here? Okay. All right. At any rate, I guess I thought the next one. Okay, yes. All right, here we go. So your block detector goes on the block feeder, not on the wire down here. You want to detect the current that is flowing through this wire right here, not necessarily this wire down here. Because if your locomotive is on the left-hand side of the block here, the current, most of the current is flowing down through this way and it won't flow down that way. So you've got to have your block current detector on the block feeder. All right, so now if you're going to have a current detector, or if you're going to have detectors, let's look at the characteristics of the detectors. There's a, a position detector, which is just one specific position on your track. And it can be done with a light beam, a magnetic, or contact. If you were an old Lionel guy like I was, Lionel had a contact that the locomotive would run over and make contact, and that's the way they detected. But or you could do weight. But this is just a position detector, and I'm illustrating it here with a photo detector with an overhead light source. So we'll call that a control point or an on-station point. And it is just for one point, such as right on your a switch, which would indicate that something is occupying the switch. It would break the light beam going down to the photo detector. Then you can have a current detector, which is what we talked about before, for an entire block. And so your block detector would look something like this. You've got your track bus coming in here, and then your block bus going out here. So this goes to your block bus on block 1, let's say. So current is going to flow from your track bus through this transformer here and out to the track bus. And you can use this for signal systems, grade crossings, automatic turnout actuation, whatever. Some of the decision criteria that you would want to have as far as selecting a detector is that it detects a decoder only. If you're DCC, again, you want to have a locomotive sitting in a block, no lights on, no sound, not moving, and just detect the power that the decoder itself is drawing. And so that's usually requires an adjustable detector. And if it's tuned to DCC, that's important too. If you're a DCC user, you want no false positives. You don't want a little spike on the railroad to trip it. So a 1 second turn-on delay would be important. You want no false dropouts. So dirty wheels, for example, if it breaks the current flow for just a split second, you don't want that to cause it to drop out. And you want any kind of signal electronics to be isolated from your track bus. So these transformer type of detectors are what you want to use. And Chubb's got them, and Digitrax has them also. And you want to be able to distribute these detectors around your layout. A lot of people who use Chubb detectors put them all in one place, and then they run their wires out to their railroad. If you got a relatively small layout, that's fine. But if you have a really large layout, having all your detectors in one place requires you to run all of your track buses out a long distance to where they're being used. So it's helpful to have these detectors distributed around your layout. And then you consider the power, dual detectors usually on one board. So here's the second bus going out through the connectors. Make sure that you have large terminal blocks so that you can accept a large wire. Make sure it has a power indicator, that it's active, detection indication, open collector outputs for your electronics, and placarded. Here's a good example of my documentation. Okay, so if you can call all of the guys who weren't interested in signal systems back into the room now that we're taking a break, a little potty break or whatever, and we're just going to talk about now generic DCC wiring, switch wiring. Here is a typical switch, and here is the pink wire, the rail A, rail B, and let's say you've got a block. Again, this is a block wiring here. You would need to break the rail joints right there for electrical purposes, and so let's talk about using a tortoise here to power it. And so now what I'm talking about at this point is, I think it's Pico that uses the term InsulFrog. They're DCC friendly turnouts, which means that the 4 rails here, the 2 switch rails at this point, and the 2 rails that go off in the frog rails, if you want to call it that, are independent electrically, and some of them have electrical connections. See the green wire here that connects the rail B here to rail B on this side, and rail B to this frog rail or switch rail right there, point rail. And it has a connection on the rail A side as well. If you don't have DCC friendly, you've got what's called ElectroFrog, I think by Pico. You're going to have to power this frog somehow or other. You could do it by depending on the point rail connecting at this point right here, but that's not recommended because of corrosion. So what I do is I have Tillig turnouts. They're really cool turnouts in the fact that they've got continuous point rails here, but these are unfriendly DCC, so I power my frogs through the contacts on the tortoise. So here, rail A is connected to one set of points on the contact. Rail B is connected, and then they have a connection to the frog. So we need, if you have ElectroFrog switches, you need to power the frog. Don't trust the electrical contacts of the point rails. And then from a signaling standpoint, the switch becomes part of the block X. Now, let's talk about circuit breakers with respect to DCC, or with respect to any layout. You have your power coming in from your command station, your booster right here, to a circuit breaker, and then it goes to rail A and rail B. And let's say you've got a switch here. And I'm going to just use an accessory decoder, although you can power the tortoises with just DC, but you can power your accessory decoder off of rail A and rail B, and then you can remotely throw a tortoise turnout or any other turnout with an accessory decoder. So let's say you bring a locomotive in and the switch and the turnout is not aligned for it. And I know none of you have done this, but I do it quite frequently. I run into a switch that's not aligned for me, and that causes a short circuit. And what happens? The circuit breaker trips. Okay, that's good. That's what we wanted to do. But now if you've got your accessory decoder powered off of that same circuit breaker, what happens is the locomotive and the accessory decoder are dead. You can't throw this switch if your accessory decoder is also powered off of the track bus. So what I recommend is a second circuit breaker and create a second DCC accessory bus and power the accessory decoder off of the separate breaker. So now let's bring our locomotive in. It causes a short. The circuit breaker for the track breaks, but the DCC accessory bus is still powered. So I can throw this turnout remotely. Notice the turnout throwing, isn't that cool? Any rate, I can throw that turnout. That clears up the short. That clears up the circuit breaker, and that allows me to run my train. So let's talk about tortoises and accessory decoders and that sort of thing. A tortoise draws about 17 milliamps. It's called a stall motor. You run a motor to an extreme until it stalls, and you're still conducting electrical current through that motor when it stalls, and it's about 17 milliamps if you've got a 12-volt power supply here, or in the case of DCC, about 14 volts. And let's say your accessory decoder draws about 3 milliamps on top of that, so it's a total of 20 milliamps to operate a tortoise-driven switch. If you've got a large layout, let's say you've got 100 tortoises at 20 milliamps each, that's 2 amps, and you put some signals on top of that, you're going to be running about 3 amps. So my point of all of this is that accessories, if you run accessories off an accessory bus, accessories draw 5 to 10 times more current than trains do. You're only going to be drawing about 100 milliamps or around 100 milliamps or 0.1 amps for a locomotive to run, whereas you might be drawing upwards of 3 amps for accessories. So separate DCC accessory bus gives you accessory power, which is independent of track power, and it gives you sufficient accessory power for many devices. So you can run a lot of different devices other than trains off of a DCC track bus. I'm going to go to an extreme and go even further than that. So we've got our track bus and our turnout and our tortoise and our accessory bus. I'm going to introduce now a DC power bus, which allows you to run cameras, monitors, lighting, and that sort of thing also. And I use a computer power supply. You can get these things for about 20, 30 bucks, and they provide 20 amps of DC power. I mean, they're amazing. And you can control them with another accessory decoder. And so I can turn them on and off remotely. And here's an example of one of my remote yard panels. You can see here a camera and monitor. Here's the monitor. And I've got lighting, downward lighting on all my panels. And so now let's get into some miscellaneous stuff. I'm a documentation geek, and it really is important to maintain good documentation. And so this is a picture from underneath my layout at one particular point. The color here is terrible, but this is your pink wire, and this is your purple wire here. So that's the track bus. And now here are block buses. These are orange wires. I picked orange for the block buses. And then here is the 12-volt DC bus, which is blue and black. Here's a picture of an IDC connector. Notice that this is the orange wire block bus, and then two track feeders come off of that one IDC connector. And there's the detector. So the track bus is going through the detector onto the block bus. And you notice these staples that I have supporting the wires and separating the wires about an inch apart. These staples can be inserted by I used a Power Fast strap gun. I don't think Power Fast is in business anymore, but the Arrow T72 works just as well. And it can support several wires in underneath one of those staples. And so when I wired my layout, I put the staples in first, and I put my rolls of wire on a little stand that I had created. Here's your pink wire, your purple wire, and then the orange block bus wire. And I used a little creeper, one of those mechanical creepers things, and I would go underneath the layout, and I could pull 100 feet of wire very easily by inserting the wire underneath one of those staples and then moving on to the next location and pulling it off of this little feeder cart that I had. So here's some other miscellaneous documentation stuff. As you saw from the previous picture, what I did, I used labels, these labels that you can get from Staples and other places, and I printed labels to go on each wire underneath the layout. So here, actually, this is in kind of reverse order. Here is P1C, power block 1C, and then I labeled the individual blocks as block 1, which came off of P1C, block 1C, and so then this is block 1 off of that detector, and I labeled those as such underneath the layout. And here's the track bus labeled similarly. Okay, that's basically, that's the end of the basic vendor independent discussion that I have, and I'm going a little bit more into detail here, and I'm going to really cruise through this stuff. For electrical engineer, you would know what different types of bus architectures, but if you're using DCC, you better be aware of bus architectures, because you've got a track bus and a cab bus and all that sort of thing. So these are several different types of buses, and I'm only going to talk about two kinds for your cab buses and control buses. I'm going to talk about RS 485, which is RS is recommended standard by the IEEE, the Institute of Electrical and Electronic Engineers. They had recommended standard for RS 485. This thing has been around for decades. And then a tree network of buses, which is a kind of a free form bus network. So in RS 485, I want to talk about this because it's important, because it differentiates the different vendors in DCC architectures. The RS 485 bus is a master slave or cold bus architecture. There is one master and everybody else that's on that bus is a slave. And the way it operates is the master will ask slave number one, what's your status? And slave number one answers back to the master, here's my status. So you could consider these slaves as being your throttles. And so your command station asks throttle number two, what's your status? And throttle number two answers back. And it keeps on doing that. It goes 1, 2, 3, 1, 2, 3. It's continuously in motion, continuously interrogating all your throttles. And so there's throttle number 3 gets interrogated. Whereas the tree architecture, tree network, is the peer-to-peer network. Any one of these devices can talk to any other device that's on the network. So this peer talks to this peer, and this peer talks to that peer, and you can be sending information back and forth across the network. So let's talk about most DCC systems other than Digitrax. They all use RS 485 architecture. So here's your command station, and let's say your booster is internal to that command station. They can be combined. But the master must poll each device to transfer data. So your master is the command station. So the command station goes out and asks throttle number 1, what's your status? Throttle number 1 answers the command station back. This is my status. And the command station knows that throttle number 1 is connected to a particular locomotive. So the command station then interprets what the throttle is saying and sends that information out over the booster to the track bus. This is your track that your locomotives are running on, and sends it to your locomotive. That's how most NCE and most of the architectures work. Digitrax is a little bit different, and I'm not advocating Digitrax necessarily. I'm just saying that they are different in the fact that it's peer-to-peer. And again, the command station and booster can combine together. And Digitrax takes the control bus, which has the DCC commands on it, and the cab bus, and combines it together into what's called the LocoNet. And I think NCE is now doing that in one cable also. It's basically all in one cable. The peer-to-peer systems are event-driven. Nothing happens unless an event occurs. So nothing is going on this command bus unless an event occurs. So let's say you have your throttle in hand and you turn it and you want to increase the speed of your locomotive. Your throttle in this system sends out a command that gets on the command bus, and the command station is listening there, and the command station says, oh, throttle number 1 wants to increase the speed of that locomotive, and so the command station sends that information to the locomotive. Notice that in this system over here, the RS-485 system, that's a 3-step process. Over here, it's a 2-step process. And so on the command bus here, you can have all kinds of other things as well communicating between each other. So you can have a computer talking to signals all on the command bus, and detectors talking to the computer and back and forth. This part up here is all recommended practice 9.2 by NMRA as far as your track bus and command bus. All of this stuff down here, as far as the RS-485 is concerned, is not an NMRA standard. It is vendor independent. And again, it just depends on the vendor as far as how many cables you have running. So at any rate, that's the end of the clinic. And I have a list of logic electronic suppliers that I've provided to Fred. And I want to just make sure you recognize that the vendors do have registered trademarks and all that sort of thing. So at this point, I'm going to stop talking and end my sharing, and let's go on for questions or whatever from the audience.